So you're probably wondering why I haven't had these three moles removed. Well, today these are going to relate to our stoichiometry lesson. We're going to be taking a look at chemical quantity ratios that are found in what we call a balanced equation. This is the specific goal for learning today. What you're going to see is we're going to learn how to interpret the quantity ratios found in a balanced equation. Down here near the bottom of the screen, you're going to see what we call a balanced equation. Let's first take a look at an analogy to make you familiar again with the concept. And so here's our analogy here. Let's suppose that we wanted to make French toast. Well, the making of French toast is very similar to chemistry, taking what we would call reactants, chemicals that we begin with, and rearranging them and turning them into what we call products. The new chemicals form from the reactants as they rearrange. In this particular example, what we have here is we have what we call the balanced equation, or similar to what we might consider a recipe. The recipe has very specific quantities in it, just like a balanced equation would. Let's assume that we have our kitchen countertop right here, and we see that we have our ingredients that we would need to make French toast laying on the countertop. So we get out our eggs, our vanilla, our nutmeg, our milk, and our bread. Now we have all the ingredients ready to begin to make French toast. Well, we're going to notice that there's a very specific quantity related to each of these particular ingredients that we might in chemistry consider actually reactants. So what we're going to see is it would require 2 eggs. It would require ½ a teaspoon of vanilla, 1/8 a teaspoon of nutmeg, 2 tablespoons of milk, and 4 slices of bread. From those ingredients, which we may think of as reactants, we ought to be able to make 4 slices of French toast, which is what we would think of as our products. And so we begin to prepare, and we get out 2 eggs. We take 1/2 teaspoon of vanilla, 1/8 teaspoon of nutmeg, 2 tablespoons of milk. We get 4 slices of bread, and voila, eventually they turn into 4 slices of French toast. Let's consider what might happen if we needed to make a different quantity, however. So why don't we assume the quantity of French toast we are interested in manufacturing or making would be 12 slices. In looking at the coefficient reveals the recipe or the ratio that would be required for all of the ingredients, sometimes thought of as the reactants, to create this quantity. In order to create 12 French toast, typically what we're thinking about is we're really just tripling this recipe. Therefore, if we were looking for eggs, since it required 2 eggs to make 4 slices, well, it's now going to require 6 eggs because we are making 3 times the quantity of French toast. Likewise, we'd have to use this measuring spoon 3 different times for teaspoons of vanilla, or ½ teaspoons, excuse me. So we would need 3 ½ teaspoons. If we looked at the nutmeg, we would need 3/8 teaspoons. In looking at our milk, we would need 6, since the coefficient was 2. And obviously, if we wanted 12 slices of French toast, we would need 12 slices of bread. Therefore, the quantity of ingredients that we call reactants relates specifically to the quantity of what we produce, in this case, French toast. So let's now apply that thinking to an actual chemical reaction. When we look at a true chemical reaction, what we look for is we look for the quantities of reactants compared to the quantities of the products. How we find that or reveal that is we look at what we call the coefficients. So on the left side of our reaction arrow here, it reveals where our reactants are. We're going to notice there's a coefficient of 2 in front of the chemical H2, known as hydrogen. We're going to notice there is no coefficient, which means there's an assumed value of 1 in front of this reactant called oxygen, or O2. When we get to the product side, we are going to notice that there is a 2. What this does is this reveals what we would call the mole ratio. We don't think about chemical quantities like we think about cooking things like French toast when we think of actual chemicals. when we think about actual chemicals, we have a number of ways to speak about quantity. One of them ways would be what we would call a mole ratio. Mole ratio simply comes from the coefficients of each reactant and each product. Let's now reveal what the mole ratio of this particular chemical equation would be. The mole ratio would reveal 2 moles of hydrogen, or 2 moles of H2, 1 mole of O2, and 2 moles of water. Once again, revealed from what we call the coefficients. These mole ratios, as you know, can be turned into other kinds of quantity. Since we recall that mole means many things, and as you look below on this particular slide, you're going to see that mole can mean what we would call particles. It could mean a mass amount, typically in grams, or it could mean a gas volume. That gas volume would be rated in what we would know as liters, as long as the chemical was at standard temperature and pressure, and we knew the chemical was actually specifically a gas. Now, since we recall that mole ratio reveals specific quantities, really all we do is we look for the quantity we're interested in. And in this particular case, we're first going to look at a particle quantity. Well, particle quantities relate to the amount that is equal to 1 mole in particles, which you remember from previous work as that value called Avogadro's number, or 6.02 times 10 to the 23rd. When we think about that, really all we do is we apply the coefficient to that value. Since that value equals 1 mole, what we'll look for is we'll look for the number of moles that relate to each particular reactant and each particular product. In this case, the quantity of reactants for H2, we see that there are 2 moles. Therefore, 2 moles times 6.02 times 10 to the 23rd reveals the number of molecules of hydrogen. In looking at oxygen, we see that there is an assumed coefficient of 1, or 1 mole. To reveal the particle ratio for oxygen, we multiply 1 times 6.02 times 10 to the 23rd. When we move to the product side where we see water, the coefficient happens to be 2. So this reveals the particle ratio for water as being 2 times 6.02 times 10 to the 23rd. They become the particle amounts revealed by the balanced equation. Let's now begin to look at what we would call the mass ratio, again, considering that there are 2 moles for hydrogen. What we pay attention to is just the formula for the chemical of each reactant and each product. In this case, the formula is H2. H2 really just means that a molecule of hydrogen is made of 2 individual atoms. Therefore, we recall that it has a very specific molar mass by adding up the mass of 2 individual hydrogen atoms. Likewise, when we look at the formula for oxygen, it's revealed as O2. This means that we would add up the total mass of 2 oxygen atoms to reveal what we call the molar mass. For water, 2 hydrogen atoms and 1 oxygen atom. What we then create is we create the molar mass for each chemical. Thinking about this for hydrogen, we see that the molar mass is 2.02 grams. However, since there are 2 moles, we multiply 2 times 2.02 because 2.02 would only represent 1 mole, and the balanced equation reveals there are actually 2. Moving on to the next reactant, oxygen, 1 mole of oxygen would be 32 grams. Since there's an assumed 1, meaning there is no coefficient in front of O2, 32 grams becomes the quantity ratio for oxygen. Moving on to the chemical known as water as our product, 1 mole of water, made up of 2 hydrogen and 1 oxygen, would have a total mass, or a molar mass, of 18.02 grams. 2 times that value becomes 36.04, because the coefficient for water happens to be 2. Looking at what we now see that if I take the quantity of hydrogen and the quantity of oxygen, the 2 reactants, and I add them, they become 36.04 grams. That becomes the same or the exact amount of mass that we had on our product side here, which means it obeys something we call the law of conservation of mass. The total mass of all the reactants, the chemicals on the left side of the arrow, should always equal the total mass of all the products, the chemicals we see on the right side of the arrow. This lets us know that we have observed or we have revealed the quantity ratios correctly when we see it obeys the law of conservation of mass. 36.04 grams equals 36.04 grams. What we'll do next is we'll now look at what we call the gas volume ratio. You can recall when we speak about the gas volume of any chemical, we remember that the quantity is 22.4 liters, equal to 1 mole, as long as the gas is at standard temperature and pressure, which is an assumption we'll need to make for all balanced equations here. You'll also need to pay attention to each chemical in terms of whether or not it is actually a gas. The symbols that follow the chemical in the parentheses usually reveal something about its state of matter. In this case, all three of these chemicals, both reactants, have this G in parentheses indicating that these are all gases. That allows us to interpret a volume ratio for each of these individual chemicals. Let's take a look at what that actual volume ratio would be, keeping in mind the exact mole amount of each. Since there are 2 moles of hydrogen, we multiply 2 times 22.4 for hydrogen, revealing an amount of 44.8. Since there is only 1 mole of the gas called oxygen, 22.4 gets multiplied by 1. And since there are 2 moles of the product called water here, we multiply 22.4 times 2, and it reveals volume ratio of 44.8 liters of hydrogen to 22.4 liters of oxygen, would create 44.8 liters of water when they combined. This reveals what we call the gas volume ratio in this particular balanced equation. You're going to want to pay particular attention to which chemicals are actually gases. Again, revealed by the G's right here. Gas, gas, gas. If a chemical is marked with any other symbol, then it is not a gas. Therefore, you will not be able to interpret a gas volume ratio for that particular chemical. Then down below here, you could simply write Na or none, not applicable, meaning since it's not a gas, there's no ratio to interpret. Let's take a look at an example that actually has this as part of a way to take a look at this. Here's a new example. Let's just clear this drawing for a second. So let's begin by thinking about what the mole ratio is. Again, keep in mind when you're thinking about the mole ratio, all you do is reveal the coefficient for each chemical. We have coefficients of 4, 3, and 2. Therefore, mole ratio for this particular equation becomes 4 moles of iron, Fe, 3 moles of oxygen, O2, and 2 moles of something called iron 3 oxide. We have now revealed the mole ratio. Next, what we can do is turn that into a particle ratio. Well, recall that 1 mole equals 6.02 times 10 to the 23rd particles. Since each of these have a quantity revealed by the balanced equation as more than 1 mole, what we then do is we reveal the coefficients and we apply those coefficients to 6.02 times 10 to the 23rd. This reveals the particle ratio if we were worried about actual particle counts. We typically ignore this type of thing in ideas in chemistry because particles are not really a measurable type of thing. So usually things like mass or gas volume become more critical because those are things that you can physically measure in the world that we live in. That's not to say that particles aren't important, because that is the reason that you're able to measure mass or able to measure volume, because particles exist. So let's begin to take a look or consider what the mass ratios would be of this. You may want to pause the video to see if you can come up with or determine what the mass ratios actually are of each of these chemicals. Again, consider what the formula would be for each individual chemical before you think about what you would write. Again, the formula for iron is Fe, for oxygen O2, for iron 3 oxide Fe2O3. That formula would reveal what we would call the molar mass of each of those chemicals, or the mass equal to 1 mole. What we come up with then is the molar mass for each of these chemicals multiplied by the coefficient. The molar mass for the chemical known as iron would reveal 55.85 grams, for the chemical known as oxygen, 32 grams, and for iron 3 oxide, 159.70 grams. Those molar masses are simply multiplied by the coefficients. Again, the large numbers written in front of any chemical reactant or any chemical product. What we then do is we take the masses of all the reactants in total, 223.40 and 96, add them, it becomes 319.40 grams. Lo and behold, if you look at the other side of the equation, that is also the total. Again, that's not a coincidence because the reactants simply rearranged in some new ratio to form these products. Therefore, they're still made up of iron and oxygen, just in a different ratio. You may want to pause to consider what to think about for gas volume below. Again, take a look at these specific symbols that are applied to each chemical up above here. That will help you consider whether or not a chemical is a gas or not. When we look at what's going on here, we actually see that the reactant that we call iron is not specifically a gas. Therefore, what I did down below here, I wrote Na. Since iron is not in the gaseous state, or it's not existing in a gas form, we cannot translate or we cannot interpret a volume for that. Oxygen, however, is a gas. Therefore, we take the quantity of 3 moles and multiply by the amount that would be equal to 1 mole, or 22.4 liters. So we do have a ratio amount for oxygen as a gas. When we look at iron 3 oxide, we see that this is also not a gas, so we apply the label not applicable to it. Let's just briefly describe what this actually means. What this tells us something about quantities that we could combine with other kinds of quantities. What I mean by that is this. If we took 223.40 grams of the chemical called iron and we combined it with 67.2 liters of a gas called oxygen, what that would do is that would create 319.40 grams of this product over here. Because oxygen is a gas, we could think about its quantity as being in the gaseous state rather than thinking about it as being in the mass state. Sometimes it's more convenient to think about a chemical in a different state of matter. However, it has to exist in that state of matter in your balanced equation. I hope you found this lesson useful related to our goal for learning interpreting quantity ratios or from the balanced equation. And I'd like to apologize for not adding more jokes to this particular lesson. But you see, I really only update my jokes periodically. Mr. Brewer signing out. Till the next time, have a great day.